Hello everyone, my name is Tomer Even. I'm a master student from Tel Aviv University. It's my pleasure to present Prefix Filter, practically and theoretically better than blue. This is joint work with Guy Evan and my advisor Adam Morrison. What is a filter? A filter is a probabilistic data structure for approximately maintaining a set of keys S from some universe U using small space. Filters are used to answer membership queries with one-sided error. The response of a filter to a membership query, does the key X belong to the set S, is as follows. If X is in S, the filter must answer query X by yes. If X is not in S, the filter usually replies to query X with no, but it might err with probability at most epsilon. The probability space is over the randomness of the filter and does not depend on the set S or the queried key X. Let's compare a filter with a dictionary. A dictionary answers queries precisely without any errors. However, storing an exact representation of S requires at least log U over S bits per item, where U is the universe size and S is the size of the set. The high space consumption of a dictionary implies that a dictionary does not fit in the main memory if the set S is too large. A filter, on the other hand, requires only big O of log of 1 over epsilon bits per item. So, if we use a filter and we allow a false positive rate of 1%, then each item requires only 12 bits, regardless of the universe size or the size of the set S. Filter's API consists of two parts, instantiation and operation. A filter needs three parameters to be instantiated: a specification of the universe denoted by U, an upper bound n on the size of the set S, and an upper bound epsilon on the desired false positive probability. Filter supports the following operations: query X, which is a membership query for an item X from the universe U, insert X, which adds X into the set S, and delete X, which removes X from the set X. In this talk, I will focus on incremental filters that supports only insertions and queries but do not support deletions. Incremental filters are useful in many applications. One such application is LSM trees that employ filters to reduce redundant IOs, namely searches for items that are not stored on disk. To this end, we create a filter for the set of keys in each SS table. Before accessing an SS table, we query the filter. If the filter says no, then we save the access to the SS table and the IO associated with the access. It is important to note that the filter saves IOs only for queries on which the filter responds with no. We call those no queries. As shown in the bottom figure, filter saves IOs only for no queries. A dream incremental filter simultaneously achieves fast build time, fast no queries, and low space overhead. Current filters support only two out of those three properties. For example, Bloom filter has a multiplicative space overhead, Cuckoo filter has slow build time, and Vector Quotient filter has relatively slower no queries. Our prefix filter has those desired properties. Our prefix filter is built upon two key ideas. The first one is to use fingerprints, which is a popular technique used by both Cuckoo filter, Vector Quotient filter, and others. At a high level, instead of storing the items of the set S, we hash the universe U into smaller universe of size n over epsilon. The image of X under the hash function is called the fingerprint of X. We then store fingerprints of items in the set S in a hash table. We note that false positive errors are caused only by collisions introduced by the hashing. Two important goals in the design of filters based on hash tables of fingerprints are small space and few memory accesses per operation. Current fingerprint-based filters are Cuckoo filter that builds on Cuckoo hashing and Vector Quotient filter that uses the power of two choices scheme. Both must perform 2 memory accesses per no query. Our goal is to reduce the number of memory accesses per no query to 1. I will now present the prefix filter. The prefix filter uses a load balancing scheme based on 2 levels that enables both fast insertions and queries. Each level stores fingerprints. The first level, called the bin table, is an array of m bins, each of capacity k. Keys are randomly hashed to the bins. The bins of the first level stores most of the fingerprints. The second level, called the spare, is an incremental filter that stores the fingerprints whose bins in the first level are full. Each bin is a dictionary that implements a data structure called a pocket dictionary, or PD for short. A PD employs the Fano alias encoding. A PD can store 25 numbers from the domain 2 to the power of 13 using 256 bits, saving 20% of the space compared to the explicit representation. One of our contributions is an efficient PD implementation using CMD instructions. Details appear in the paper. We first focus on the first level of the prefix filter. Let uppercase FP of x denote the fingerprint of x. We interpret uppercase FP of x as 2 hash functions, bin of x and FP of x. Bin of x maps x to one of the bins. We refer to lowercase FP of x as the mini fingerprint of x. At a high level, the bin table attempts to store the mini fingerprint of x in the bin of x. Our main contribution is the prefix invariant from which the name prefix filter is derived. This invariant enables 92% of the operation to complete with one single memory access. When a key x is inserted, we add its mini fingerprint to bin x. If bin x overflowed, we forward one fingerprint from bin x to the spare. Which fingerprint from bin x is forwarded to the spare? A naive solution is to forward the newly inserted fingerprint, which is FP of x. Our key insight is to forward the largest mini fingerprint, so that the bin contains a maximal prefix of the smallest mini fingerprints. To see the benefit generated by the prefix invariant, consider a no query. A naive approach requires searching for x in both levels if bin x overflowed. The prefix invariant requires searching for the spare only if bin x overflowed and the mini fingerprint of x is larger than all mini fingerprints currently stored in bin x. This dramatically cuts down the number of access to the spare. Specifically, we prove that less than 8% of the no queries need to access the spare. Another contribution of our work is the mathematical analysis of the prefix filter. We rigorously bound the filter's false positive rate and the probability that an operation requires accessing the spare, and hence more than a single memory access. Importantly, our analysis isn't asymptotic, so it does not hide constants and works for practical values of the set size m. Our analysis studies x, the number of fingerprints forwarded to the spare. We provide an exact expression for the expectation of x and also show that x is highly concentrated around this expectation. This allows us to bound the event that too many fingerprints are forwarded to the spare, and from that the probability that an operation will access the spare. I will now present an empirical evaluation of the prefix filter. We start with an experiment that evaluates filters under varying load. We initialize the filter to support a set of roughly 250 million keys. The experiment then proceeds by gradually inserting the keys in increments of 5% and measuring the insertion throughput as load increases. After loading each 5% of the keys, we measure the throughput of uniformly random queries at this load. Due to the universe size, uniform queries are in fact no queries. Finally, we measure the throughput of yes queries at this load. We evaluate and compare the prefix filter to Bloom filter, the cuckoo filter, and an implementation of the VQF or vector quotient filter using our improved PD structure, which we called two-choicer. The two-choicer has 26% higher no-query throughput than the VQF, which is why we use it. We know that since the spare is in fact a filter, we also use the two-choicer as the spare in the prefix filter. After explaining the experiment settings, we move on to the results. The Bloom filter expected number of probes increases as the filter fills up to roughly 2 memory accesses per query in expectation, making the Bloom filter slowest for no queries. The Cuckoo filter's no query throughput is steady, as it always performs the same computation per query. It also has the fastest positive query throughput. The no query throughput of the two choicers declines by 31% as it fills up. The prefix filter has the fastest no query throughput. The no query throughput of the prefix filter declines by 46% as it fills up. Here we show that the time required to populate an empty filter with roughly 250 million keys. The prefix filter has the fastest build time. The prefix filter is 2.3 times faster than the Bloom filter, 3.6 times faster than the Cuckoo filter, and 1.4 times faster than two choicer. To summarize, we propose the prefix filter, an incremental filter that offers space efficiency comparable to the state-of-the-art filters, fast queries comparable to those of the Cuckoo filter, fast insertions with overall build time faster than those of the vector quotient filter and Cuckoo filter, rigorous analysis of the prefix filter properties that holds even for practical values. We also empirically evaluate the prefix filter and demonstrate its qualities in practice. A public implementation of the prefix filter in C++ is available at GitHub at the following link. Thank you very much for your attention.